Everybody, this is Mr. Beckstrom, and today we're going to be taking a look at section 5.1, which is approximating areas under the curve, and more specifically, we're going to be taking a look at Riemann sums. So let's first kind of look at the definition here and break it down and make sure we understand what they're actually doing. So suppose the closed interval AB is a closed interval containing n subintervals, right? So we have x equals a here, we have x equals b at the end, we have some curve here, right? And we want to estimate the area under the curve between a and between b. Well, one way that we can do it, and one way that they did it, is that they divided that interval into equal subintervals. So here they did 1, 2, 3, 4, 5, 6, 7, 8. They did 8 equal subintervals there. That would be your n. So n would be 8 in that case. And they used some value in each one of these intervals as the height for a rectangle. So for example, in this first interval here, they used just this kind of arbitrary random point here and made a rectangle that went up directly to the point. So the x value went right up to the point on the curve, and then they made a rectangle. And then they found the area of that rectangle. And they did the same thing for each one of these. They just picked some point in there, and then they went up to the top wherever they picked that point, and they found the area of that rectangle. What they said was that the area, if you add up all of those rectangles, the areas of all of those rectangles, that it should be pretty close to the area under the curve. It's going to depend a lot on which x value they picked, and hopefully, they'll have some over amounts like you see here and here, and they'll have some underreported amounts like here and here. But when it adds all up, hopefully it shouldn't be too far away. And so that's what they're doing. Now the idea, in order to the whole idea of calculus, is to make these subintervals smaller and smaller and smaller. Therefore, eventually, as the width of those rectangles oh my gosh, we were talking about that forever, approaches 0, then we're going to eventually get really, really, really thin rectangles, and all of this underreported space and all of this overreported space is going to be gone, and we're going to end up getting the exact value of the curve under the curve and between the two values that we picked in the interval there. So of equal length, so delta x. So if you take this value minus this value and you divide by the number of subintervals you want, that's going to be the length of each one of these, or the width of each one of these, whatever you want to call it there. The endpoints are basically the endpoints of each of these subintervals there. And then, let me see here, the endpoints of the subintervals are called the grid points. So those are also called the grid points. I don't use that term very often, but you're welcome to do it. And they create a regular partition of the interval a to b. In general, the kth grid point is k is equal to a plus k times delta x. So if you start with a here, and you want to know, let's say, the fourth interval, that would be whatever your value is for a plus 4 times the delta x. That's the width of your subinterval there. So 1, 2, 3, 4, and that should be your fourth one. All right. Let's take a look at how we can do different types of Riemann sums, and we're going to be looking at left Riemann sums, right Riemann sums, and then where we use the midpoint. And this is before we let the width of them approach 0. so let's go ahead and take a look at how we define these left Riemann sums, right Riemann sums, midpoint Riemann sums, and then we'll look at the formulas in order to calculate the approximate area under the curve using them. So a left Riemann sum here means that for each of our rectangles, for each one of our rectangles, we're going to use the left side as our height, our left side. So if we're doing a left Riemann sum with this one, this first rectangle here would actually go up a little bit higher until the left side of it just reached the curve, and then it would be a little bit more like this. So it would come up a little bit more here, then it would come over there and down there. So that would be a left Riemann sum. A right Riemann sum would be where the right side of these rectangles went right up to the curve and then came over, and then came over once they hit the curve. So this last one, a right Riemann sum, would be where, and it would be for each one of these. So right Riemann sum, you'd use the right side of each of these rectangles in order to calculate your height. And the midpoint, just like you may guess, would be using the midpoint between both the left and the right sides of these triangles as your height. All right, so let's go ahead and try to work an example here. So let's go ahead and take a look at the function of cosine of x on the interval from 0 to pi over 2. So if I was going to draw a little bit of a graph here, like this, we know here's 0, here's pi over 2. It starts up here at 1, and it comes down here. So we're looking for this curve here between 0, 1, and then pi over 2, 0. So this is the curve that we're looking for, the area of the curve that we're looking for. And they want us to break it into 4 sub-intervals. So let's do both a left Riemann sum and a right Riemann sum for this. So go ahead and pause the video now, see how far you can get, and then unpause it, and we will go ahead and go through the solution. Okay, so first thing I'm going to do is try to draw a little bit better of a picture so we can break this thing up into rectangles. So I'll put it over here. Oh my gosh, I'll draw a straight line. And it was close enough. All right, so here is 0, 1. Here is pi over 2. And here is my curve there. So they want us to break this up into 4 equal parts. So I'll do it in half, and then in half, and then in half again. So the first time that we do this, we are going to do a left Riemann sum. So for each of these rectangles, I'm going to use the left side of it to get the height. So the left side of the rectangle is going to go right up to the curve, and then it comes over. So for this one, you go up to here, and then you go down there. For this one, you go up to here, and you go down there. And for that, and I'll probably make that one a little bit better. Yeah, that still wasn't better, was it? Yeah, a little bit better here, and then the last one. So I can already tell that if I use the left side of each of these rectangles as my height, that I'm going to get an overestimate because I have a lot of extra space that's on top of the curve. So let's go ahead and figure that one out. So what we do is we evaluate the function at each one of these points here, starting with this one, because starting with A, because our left side is the height. So for example, it would be, before I do that, let's actually figure out what our delta x is. So our delta x, which we're going to need, remember from earlier, is B minus A over N. So that's the width of each one of these rectangles. So in this case, that's going to be pi over 2 minus 0 all over 4, and that's going to just giving us pi over 8. So that means the width of each one of these rectangles is going to be pi over 8. And if we added pi over 8 4 times, we get 4 pi over 8. And that's the same thing as pi over 2. So that's that. And then we want to calculate our 4 endpoints, or the ones that we're going to use for the heights of these rectangles. So we know we're starting right here at A. So we're going to be using 0, starts here. And then this one is pi over 8 to the right. So you just add pi over 8 to 0, and you get pi over 8. You add another pi over 8, and you get 2 pi over 8, which is pi over 4. And then for this last rectangle here, we're using this value, that you add another pi over 8, and you're going to get 3 pi over 8. So these are the points, the x values that we're going to be evaluating in the function to calculate our height. So the formula is, this is a summation formula. We're going to go from 1 to 4, so 4 times. We're going to evaluate each one of these and multiply each one of those by our delta x, which is the pi over 8. That's basically just finding the area, length times width of each one of those rectangles and adding them together. All right, so let's do that. So this is going to be, the first one is f of 0 times pi over 8 plus f of pi over 8 times pi over 8 plus f of pi over 4 times pi over 8, and finally plus f of 3 pi over 8, 3 pi over 8 times pi over 8. All right, now these pi over 8s, instead of getting exact values here, which we could by using a half angle or a double angle formula under cosine, I'm just going to go ahead and evaluate this in my calculator. So I'm going to pull out a pi over 8, a pi over 8, and then it's going to be f of 0 plus f of pi over 8 plus f of pi over 4 plus f of 3 pi over 8, 3 pi over 8. All right, so I got that. Well, now let's go to my calculator. So I'm going to go ahead and put my function under y equals. So that's going to be, we said it's cosine of x, right? Yep, cosine of x. So just cosine of x. Enter. Let's make sure that we are in radians, which we are. And now I'm just going to do this. I'm going to do my second pi over 8. And we're going to multiply that by, and this is where it's going to get a little bit cool. All right, so I'm going to hit vars, y variables, y1. So I'm going to take that y1 function I just put in there, evaluate it at 0, plus vars y1 evaluated at pi over 8, plus, same thing, the y variable evaluated at pi over 4, and plus evaluated at 3 pi over 8. 3 pi over 8. Do I need to put that in parentheses? No, because it'll do order of operations there. So one, close it up, and let's see what we get. So we get about 1.183, about 1.183. So this approximation is about 1.183. that was a lot of work. A lot of work. Now, if I were to use the right side, then instead of starting with f of 0, right, I'm going to start with f of pi over 8, and I'm going to end with f of pi over 2, right? So it's going to be the same formula, right? Except this time I am going to start like with pi over 8, and then we're going to end with pi over 2. So instead of this term here, we're going to replace that with f of pi over 2. So if I'm using my calculator already, and I do second entry, I pull that up here, really all I have to do is just go to my very first term here, and instead of y over 0, that's going to be y of pi over 2. So second insert, second pi divided by 2, and let's get rid of that 0 there. So it's the same thing, except this time we're using the right endpoints of each of those rectangles, which means that we need this y of pi over 2 in there, and we need the y of pi over, or the y of 0 out of there. And when I put that in, I get 0.791. So this is the left Riemann sum, which we already figured out was an overestimate. This is the right Riemann sum, right? Riemann sum, which is approximately equal to 0.791, 0.791. Let's take a look at what that would look like. Starting here at 1, going to pi over 2, and using, so we divide it into 4 subintervals. Now we're using the right side as our top. So this isn't even going to give us anything, and then we're going to go up here, there, and then we're going to go up here, there, and then we're going to go up here. So in this one here, you can definitely see that that is a huge, not a huge, but a pretty large underestimate, because we have a lot of missing space that we're not taking the area of. So we know our answer is somewhere between here and there. And just so we feel a little bit of satisfaction, I'm going to go ahead and do a definite integral a little bit early than I should, but I want to find out what the exact area is. All right, so to find the exact area under the curve, I'm going to set up a definite integral going from 0 to pi over 2. Definite integral going from 0 to pi over 2 of the cosine of x dx. All right, now the antiderivative of cosine of x is positive sine of x. We saw that from the last section, because if the derivative of cosine of x is negative sine of x, then the antiderivative is positive sine of x. So this is going to be sine of x evaluated, and when we do the definite integral, we don't need the constant of integration, because those are actually going to subtract out. So this is going to be evaluated from 0 to pi over 2. So we take the antiderivative and we evaluate it from these limits of integration here. And this works like this. We do the antiderivative evaluated at the upper limit, pi over 2, minus the antiderivative evaluated at, and this is actually the fundamental theorem of calculus that I'm doing here, which we're going to be looking at very soon, minus value at the lower limit, and you'll see that the sine of pi over 2 is 1, minus 0 is equal to 1. So you can see the exact value under this curve is 1, which is right in between our left Riemann sum and our right Riemann sum. All right, everybody, I hope this helped. If you have any questions, let me know, and have a great rest of your week.